So we saw in the last video that you can sort of think of the 3 showing up in our infection model here as an infection rate. And yeah, maybe that's a misleading term a little bit, since, I mean, couldn't you call x prime an infection rate? X prime is the rate at which the number of infections increases. Sounds like an infection rate to me, but no, people would refer to the 3 here as the infection rate. So that's not number of new infections per day, but we saw it has units of inverse days, or inverse whatever the time units are. Now, I just sort of randomly put 3 here. The reality is what should go here just depends on, you know, how infectious the disease is, right? Or rather a combination of things, how infectious the disease is and how vigilant people are being about not spreading it, and so on. Let's now, instead of just randomly putting 3 here, let's put an unknown parameter r. So here, r is a constant. That's not clear from just writing the differential equation like this. Let me write it in full non-lazy form, where you can see where the time dependence is. So notice I wrote x prime of t, x of t, but I didn't write r of t. I could have, but that just wouldn't be the same model that I want to look at. Here, r has no time dependence, it's just a constant. It's an unspecified constant. Okay, so what happens when we try to solve this differential equation? Well, we can use the same trick that we used before. You know, x prime over x equals r. So the derivative of log x equals rt, possibly plus a constant. So log x, getting ahead of myself. The derivative of log x equals t, and equals r, and so log x equals rt plus a constant. So you can think of that step as integrating both sides, or as, you know, just trying to think through the problem of if log x is something whose time derivative is r, then what could log x be? Well, the only things that have time derivative r are functions that look like rt plus c, where c is a constant. Then we exponentiate both sides, and we get e to the rt plus c. Then we write that as e to the c times e to the rt. And then we look at the e to the c and we say, well, that's just a constant. If c is a constant, e to the c is a constant. So we might as well just say x equals a e to the rt, where a is just some constant. All right, so now we have sort of, starting from a differential equation with a parameter in it, we came up with a general solution which has that same parameter in it. So we have sort of solved all possible x prime equals something x type equations. So it has the same parameter showing up there. But it also has this parameter, which is what makes it a general solution. That parameter a is to help us describe the family of all solutions to the original differential equation. If I give you an initial condition, then that will specify a, but it will not specify r, right? R is just kind of a parameter in the overall setup. So one reason that I'm showing you this is that the word parameter often confuses people. It's really overused. Here it's being used to refer, you could refer to this as a parameter because it parameterizes the family of differential equations that you might be considering here. For each choice of r, you get a different differential equation. And then here you might call the a parameter because it parameterizes the family of solutions to a given one of these. So pick r, get a differential equation here. Pick A, get a particular solution to that differential equation. Because there are two parameters, because there are two things to pick, we say that there are two parameters. So this is a two-parameter family of functions. All right, most of this is just to get you to pay attention to the roles that different constants play that show up. So pay attention to the fact that while A and R are both constants here, A is playing a very different role. A parameterizes the family of solutions. And to determine A, you need an initial condition. So, and R is sort of a parameter on the overall model. So fixing R has to be done sort of at the top level. Yeah, so let me show you some examples of what this would look like in Mathematica. Okay, so here's our the same Mathematica thing that I showed you earlier. And I'm just going to change the 3 here to an R. And that's our solution, general solution over here. And of course, if I plot this, I'm not going to see anything because it doesn't know what R is. But I can create a bar for R to manipulate the values and watch what happens to the solution. So let's say I'm going to vary R from 2 to 5. So here's my exponential growth. This would be, so A is set to 30 here, and R is set to 2. So that what you're seeing is the plot of 30 e to the 2t. And if I vary A, then you can see solutions to the same differential equation, namely x prime equals 2x, but they all have different initial conditions. You can see, so here's time 0, and wherever the graph intersects the vertical axis here, that's the number of infections initially. So here what I'm changing is the initial conditions. On the other hand, if I move this bar, then I'm changing the differential equation. So here's r equals 3, what we had before. And, these are all different fixed initial condition, but different differential equations. So, for example, here's a solution to the differential equation x prime equals 4x, 4.046x. And now for that differential equation, I can look at a whole family of solutions.